Nothing in nature changes without a cause. A body at rest will remain at rest until acted upon by an external force. That's the law of inertia. The same reasoning holds for a body in uniform linear motion, since there's no significant distinction between rest and uniform linear motion due to the relativity of motion. In physics, these concepts must be expressed mathematically. To make the idea easier to understand, let's look at the motion in one dimension. When force is applied to the body, the change in velocity per unit of time should be a measure of change in motion. Force is clearly a cause of the change. The change in velocity over time is acceleration. Let's mathematically connect cause and effect, applied force F and resulting acceleration A. The greater the applied force, the greater the acceleration. We know from experience that the acceleration of a body decreases as its mass increases. Thus, the addition of mass to proportionality yields the equation A equals F over m. This equation is widely recognized as Newton's second law of motion, or the fundamental equation of dynamics. The concept of force, once merely an idea, is now defined mathematically. Additionally, this equation conveys another important concept. The mass of an object indicates how strongly it resists changes in motion. The mass quantifies body's inertia. If we consider an alternative perspective, the body's inertia defines its mass. This is inertial mass. There is another definition of mass, gravitational one, but we'll discuss it some other time. Inertia can create the illusion of pseudo-forces in a system that is accelerating. Consider a bus moving uniformly in a straight line. If the driver suddenly applies the brakes, the bus will come to a stop, but the passengers will continue moving forward in a straight line due to inertia. This is the perspective from the outside. However, inside the bus, passengers feel an invisible force acting upon them. That's an inertial force. What makes the difference is the frame of reference. If the reference is an accelerated system, the laws of motion must be complemented by inertial forces. Enough of inertia. Let's get back to the Newton's second law of motion. Substituting acceleration into the fundamental equation of dynamics yields F equals m times delta v over delta t. Since an object's mass doesn't change when it moves in classical physics, we can factor out the symbol delta before the mass m without affecting the expression's validity. Thus, force is equal to the change in the quantity m times v per unit of time. This quantity was termed quantity of motion by Sir Isaac Newton. Today, we recognize it as a linear momentum p. The fundamental equation of dynamics can now be expressed as F equals delta p over delta t. Since both force and momentum are vectors in three-dimensional space, the vector equation must be used. If there's no change in the linear momentum of an object in motion, then no external force is acting on it. Conversely, if no external force is present, there is no change in linear momentum. This principle also applies to a system of two or more bodies. If no external force acts on the system, its total linear momentum remains unchanged. This is known as the law of conservation of linear momentum. From the above, it follows that if the system consists of two bodies with linear momenta p1 and p2, the total linear momentum will not change even after their collision. If we substitute delta P from the fundamental equation of dynamics, delta P equals F times delta T. Considering that the change in the first linear momentum, delta P1, was caused by the force exerted by the second body on the first, F21, and that the change in the second linear momentum, delta P2, was caused by the force exerted by the first body on the second, F12. Introducing these quantities into the expression for the conservation of linear momentum yields F21 times delta T plus F12 times delta T equals 0. After cancelling delta T, we find that F21 equals minus F12, which is Newton's third law of motion. If the first object exerts a force on the second object, then the second object also exerts an equal and opposite force on the first object. Thanks to Sir Isaac Newton, all of these concepts were introduced to physics in the 17th century.